welcome back to the second part of my 555 timer explanation in a nutshell. In the first part I've explained about this section here, the theoretical things you need to know about the timer, what it's used for, and how to use it, and the different modes. And in this part we're gonna look at some practical applications to the knowledge that we covered in the first part, just to see how we utilize it. And the easiest example to show you would be if we look at these two timers here. They are a stable mode and a duty cycle below 50%. And we're going to use them to drive a servo motor, which I have here. And I'm just going to connect it. And in the meantime, I just shorted out everything, but it's okay. In the first part, we talked about the duty cycles and the frequency pulses in monostable mode. And now we're going to use this information to control this servo motor. Now if you look at the specs of a servo motor, you'll see that in order to communicate with it through this signal pin that it has inside in the controller, you need to send a signal which is at a certain frequency, a specified frequency or a range of frequencies, with a certain duty cycle. And that's what we're trying to achieve with the configuration of the 555 timer. So starting with this circuit here, I've configured it in such a way that it produces a signal of 19 Hertz and a duty cycle between 2 to 6%. Which is needed to control the servo motor. I've added two buttons, and each button will feed a different value of R1 into the circuit. So now nothing happens, it's just on, and it's not that it's oscillating or anything, because I can show you this if I just connect an output here, and I will connect it to my binary counter. We can see that nothing happens. So again, it just provides a high, and it's not producing units. If I press one of these buttons, we can see the LED flashing at the rate that the signal is produced, and also we can see here that the binary counter has moved. But just as you saw, when I press the button, I am producing a frequency of 19 Hertz with a certain duty rate according to the values of R1, which I'm feeding with each button. And that causes the servo motor to position itself at a certain position. So let's look at it from on the calculator, just to calculate the values that I've used here in this circuit. So first of all, since we're working with below 50% duty cycle, I'm going to set it to that mode. And for R1, I've used, let's take the lowest value, which is 56K. And for R2, 3.3 mega ohms. And the capacitor is a 22 nanofarads capacitor. And we get the frequency of 19.54 Hertz at a duty cycle of 1.6%. And if I press this button, you can still see an indication on the LED of what actually happens, the signal that comes out. And if I set the higher value, which is 110 on R1, 110K resistance, then I'm producing a frequency of still 19 Hertz, 0.23, with a duty cycle of 3.2%. So that the change in the duty cycle, that 1.5 or 2% that we go higher and lower, that is the signal that tells the servo motor at which position it needs to be at. So in order to create an efficient circuit, not this one like here, which I used minimum parts, you need to be able to change R1 and R2 in order to stay within the same frequency range and still be able to change the duty cycle between 2%, 2 to 6%. That's the whole idea. The second circuit that I have here, I'm just gonna connect this one. It does the same thing. It's meant to control the servo motor, but it's using different values. So here, for example, I'm using a 22 nanofarads capacitor, and here I'm using a 471. Here for R2 I'm using 3.3 mega ohms, and here I'm using 150K for R2. And also my inputs for R1, they range between 3.3K and 4.3K. So while here we had a range of let's say 70K, here we have a range of 100K, which decide at which position this servo motor will go to. And you can see that by pressing the button. It doesn't work that well because, again, we have a very narrow scope of working to get an exact range, and that becomes very difficult when you work at just 1000K. But this is just to show you that we can produce the same results, but using different setups of the 555 timer. Now if I want to make this a bit more efficient, let's say, I'm going to connect this circuit back. And this time, instead of using the buttons, I'm going to be using a pot. And it's in this circuit, it is 100K. You can already see that it's flashing. Right now, it's producing a signal which is maybe above the frequency a bit or below, and the duty cycle doesn't match, so nothing happens with the servo. But once I adjust this value, then you can see that it reacts, and it has a very narrow range of about 50K. But this is what we're doing. We're doing the same thing just like with the buttons, only instead of feeding two hardwired values using resistors, we're using a pot to change this setting. And in this circuit, we have the same thing, but instead of using a 100K pot, I'm using a 10K pot, and it gives the same effect, but again it has this narrow, and I need to connect it obviously, but it has a very narrow range that we can work in, and here you can see it. So I need to move the pot really just a tiny amount to get to a sort of full range, but it's not stable, so you get this choppy result. So obviously this circuit that gives us more range is better than this one. So that concludes this part about how to actually put that knowledge into practical use. And you saw how everything we covered, the frequency, duty cycle, how to calculate it, we applied it into moving that servo motor. The last circuit that I have here that we're going to talk about. For starters, you can see that unlike all the rest of the timers here, where we have This is just monostable, but we have 3 that work on 1 Hz frequency. These ones, they already work on 19 Hz frequency. But this one, the LED is just on. And does it mean that nothing happens here? Well, we can test it just to show. So I'm going to connect an output here and feed it to my binary counter, and you can see that this time it doesn't just stand still, but it actually counts. And on the counter itself you can see the speed that it's counting, where we can still have some indication from the LEDs, where you don't have this here. So here it's just constantly on, but this timer is configured to work at around 263 Hertz. Those are the values that I've used here. We have a 68 nanofarad capacitor, and these two I don't remember now, but they're set up just like you saw to produce a certain frequency. Since we can't see anymore an indication on the LED, which is just for example's sake, yeah, this is nothing practical that you will do with it, but we see no indication on the LED. We can move to another method of, let's say, visualizing, or, well, not visualizing, but the other method would be listening to the signal that actually comes out. And for that I placed a small speaker here, and I'm going to connect an input to it. And just to see, let's first start by listening to what a 1 Hz output signal would sound like, and we will take this example here of about 50-50. And once I connect it, you can hear that there are these clicking sounds. No tone is actually being produced, and you can hear that that the sounds correspond to the way that the LED here flashes. So you're hearing the on and off states of the signal. And the same goes if we take this one, for example. You can hear that there are 2 clicking sounds very close to one another, and that a small time gap between them, that's the off state that you see on the LED, and the rest of it is the on state. And if we set the speaker to one of these 2 circuits, let's take this one. So we can see that right now we're producing already something else. It's not just clicking noise, but it has a higher frequency, 19 Hz, but still it's not really a sound. And the same goes for this one. They again work on 19 Hz, but they don't produce any sound, just these clicking noise of the on and off state, which you can see on the LEDs. Now in this case, where I'm using the timer configured to work at 263 something Hertz, then you will hear a sound like this, which is basically all those clicking sounds very fast, but that already turns it from clicking noises into a tone where we cannot distinguish the on and off between those clicks here. And if I remove the R1 transistor and I replace it with just a 100K pot, so that I can play around with the value that I'm inputting here, I will set the speaker. I will connect the speaker to the output. And right now, what you're hearing is me changing the input value of R1. But what it means, when we change the value of R1, supposedly that everything here, R2 and the capacitor stay the same, If we set the value higher in comparison to R2, we are lowering the frequency and we are increasing the duty cycle. So this is basically what you're hearing. You're hearing a lower frequency with increased duty cycle. If we will change the capacitor here, it will not affect the duty cycle, but it will increase the frequency or decrease it. The lower the value of the capacitor, the higher the frequency. And if you can see it right here. So I've replaced the capacitor. I had a 68 nanofarads and now I'm using 47 nanofarads. And there will be a change in the tone. So this tone has a much higher pitch than the previous one, and that's because we are at a higher frequency. Right now we are at something 310 or something like that. The R2 capacitor, resistor, sorry, so long as the capacitor doesn't change and let's say R1 doesn't change, if we change the value here, the lower it is in comparison to R1, the higher the frequency will be and the lower the duty cycle. So this is how the two resistors and the capacitor affect the timer in producing the signal. And that's pretty much it. The idea from covering this part is that if you want to produce again an efficient servo driver, let's say, then you need to be capable of changing both the values of R1 and R2 in this 555 timer configuration, obviously. But this is what you need to achieve without changing C1, the capacitor. So always staying on the same frequency, but only changing the duty cycle in the circuit. So that's it. I've covered everything that I want to cover about it. I hope you like my explanation, and I hope you like my channel. If you like it, please subscribe. Always makes me happy. And that's it. You will find resources, the link to the first part, and the link to how to produce these stable mode circuits in the description. And thank you for watching. I'll see you next time.